Welcome to the Optical Emission webinar organized by Avantes. Before we start, we would like to tell you something about logistics by using the webinar. On your screen you see the control panel. All attendees are muted, so you are not able to respond by voice. If you have questions, please use the chat box on the right of your control box. If there are any problems, you can enter it now in the chat box so that we can fix it right away. Your questions will be answered at the end of the session. No problems are arised, so we will continue with the webinar. The agenda of this webinar is: first, we will give you an introduction to Avantes and spectroscopic solutions. In the second part, we will go in depth and tell you more about optical emission spectroscopy. This will be done by Professor Daan Schram of the University of Eindhoven. And at the end, we will answer the questions asked during the webinar. Let's start off with the introduction into spectroscopy. Spectroscopy is a study which deals with the methods of measurement of light. So within the Avantes spectrometer range, this relates to the range of 200 to 2500 nanometers. Since the invention of the spectrometers way back in 1819, spectrometers have come a long way. As with computers filling a complete room in the early days, nowadays the spectrometers are miniaturized and they have performed equal or better than the bulky ones 15 years ago. Our goal is to continue this way, so that in the end a spectrometer can be seen as a smart sensor and integrated in various devices. Light is around us in many forms. It can be used in a romantic candlelight, or the LEDs on your equipment, or the incandescent light bulb, or perhaps the lasers in the DVD player or the CD player, but also in plasmas like the sun. Light is all around us. Here you can see an overview of the electromagnetic spectrum. Starting from the gamma rays, through the X-rays, into the spectrum detectable by our spectrometers, up to the radio and microwaves. Enlarged, the 200 to 2500 nanometer section, detectable by our spectrometers, showing the UV part, the visible part with all the belonging colors from blue to red, and the near-infrared part, which is of course not detectable by the human eye anymore. A spectrometer is an instrument which is used for separating the components of light, which has different wavelengths, more or less like a prisma does. Here you can see the function of the prisma with a white beam coming in, separating in all the separate colors. Here, a spectrometer in its most elementary form, consisting of an entrance tube, a prism, and an observer tube. Luckily, spectrometers have been improved over the years. The Avantes spectrometers are miniaturized fiber-coupled spectrometers and are based on a symmetrical Czerny-Turner optical design. Light enters the spectrometer through the slit at the left bottom, and this slit will be projected on the CCD detector on the left top corner. The incoming light gets collimated by a mirror before it hits the grating. This grating is the dispersive element which separates the light into its separate components. The focusing mirror folds the light path, and in the end the light is shed on the CCD array, consisting of multiple pixels. So the most important elements in the spectrometer are the slit, the mirror, the grating, the focusing mirror, and the detector. As mentioned, the grating is the dispersive element of the spectrometer. Same as with the prisma, it diffracts different wavelengths under a different angle. As you can see in this drawing, there are also direct reflections and other orders present. The design of the optical bench is in a way that this unwanted light will not be projected on the detector, and therefore causing false readouts if it would happen. The slit at the entrance is one of the parts which determines the optical resolution. The projection of the slit will be projected over multiple pixels. The less pixels it will be projected on, the better the spectrometer is able to distinguish two separate wavelengths close to each other. So a narrow slit will give a higher optical resolution, but at the cost of intensity. Since one is interested in the wavelength of the components and not the pixel of the detector which are illuminated, the spectrometer will be wavelength calibrated. This is done by presenting a light source with known peaks to the spectrometer. This way a conversion function can be determined between illuminated pixels and actual wavelength. In summary, this is what will happen inside a spectrometer. A light will emit light. The spectrometer timing control will tell the CCD to gather the light during the integration time. And after the integration time, the light will be transported to a buffer, digitized by the AD converter, processed on the board, and transported through USB cable to the computer, where it will display a spectrum on the screen. This spectrum, we call it scope mode, is actually raw data. And one needs to be assured that this raw data does not necessarily mean it has to relate to reality in all its aspects. In this mode, response curves of all optical components like the detector, the grating and the mirrors, or perhaps even the fiber used, are present. So this mode with raw data can be used to obtain wavelength information like peaks in emission spectroscopy, or optimize the spectrometer settings for the other modes. These are typical raw spectra of a spectrometer. Spectrometers can be used in various setups, enabling multiple applications. Some of these setups are, like this one, the transmission setup, where light hits a sample and the spectrometer measures the light transmitted through the sample. Or in reflection mode, where the light impinges upon a sample and only the reflected part is measured by the spectrometer. Or absorption mode, similar as in transmission mode, but now the information is valid which is obtained by the sample, absorbed by the sample. The fourth mode is irradiance mode, where we measure light emitted from an object. Here we see an important part. In order to measure light intensities in a good way, one needs to intensity calibrate the system. At the right bottom corner, you see a typical spectrum of a halogen light source with a smooth curve going up from 350 nanometers far beyond 2000 nanometers. When one observes the same light source with a spectrometer and only displaying the raw data, one will see a graph as displayed in the left top corner. So one needs to determine a translate function which translates the raw data from the left top corner to the absolute data at the bottom right corner. This is what we call an intensity calibration. By doing this, in the spectrometer, a calibration transfer function can be stored so that all raw data can be immediately converted into intensity calibrated data. And this way, one can relate intensities from one wavelength to the intensity of another wavelength. In a formula, it looks like this, where you can see that the sample data is manipulated by the transfer function here called CalData. Spectrometers can be used in a lot of applications, like there are LED measurements, or measurement on solar panels, or measuring the simulators impinging light on the solar panels, measuring the coatings by thin film measurements, or doing blood analysis and determining the level of oxygen or hemoglobin, or used in fire detection. The applications are endless. But one important field is the optical emission spectroscopy. Emission spectroscopy is a technique where one examines the light coming from the sample, and by measuring the wavelength of these photons emitted by the atoms and the molecules, one can determine the fingerprint of the element. So each element has its own characteristic wavelengths which are emitted, and with this fingerprint one can tell more about the elemental composition of the sample. In this example you see the hydrogen spectrum. Each of these frequencies are related to the energy by a formula. E photon equals h times v, where E photon is the energy of the photon, h is the Planck's constant, and v is the frequency, where the frequency is also equal to the speed of light divided by the wavelength of light. So you can see the energy of the photon is directly related to the wavelength of the light emitted. The frequencies of light that an atom can emit are dependent on the states the electrons can be in. When excited, an electron moves to a higher energy level, but when the electron falls back to its ground level, light is emitted. This is a general introduction to spectroscopy. Now we will go to Mr. Daan Schram from the University of Eindhoven to go more in depth.
It is a pleasure to contribute to this web seminar by giving a more in-depth talk about the analysis of plasmas by absolute emission spectroscopy. This analysis is also performed to analyze specific application areas as deposition and etching. It's based on work by Hanen and Leite Gonzalez and on the work of Harskamp under the leadership of Richard Engel, and on earlier work in magnetized and expanding plasmas in the groups ETP, PMP of the Faculty of Physics of the Eindhoven University, leaders by Van der Zande and Kessels. It is a plea for absolute emission spectroscopy. We know that there is a history in astrophysics, And the history in astrophysics is not much more what one can do. One can look to the stars and observe the radiation. And this radiation is at first all we have to analyze what is the composition and properties of stars, interstellar matter, and molecular clouds, etc., to radiation. And on the left there is the excitation scheme of hydrogen atom, already mentioned, and indicated is the first Balmer light in red, in which also the picture is taken on the right hand side. One thing I'd like to make clear from the beginning, that in many cases plasma is inhomogeneous and one has to analyze. And the reason is that usually the plasma is somewhere ionizing, but in larger where the power is fed to the plasma, but in other parts it is recombining. The radiation is of other nature, you will see. What can we see in plasma chemistry? Now, we like to know which species, but I will tell you not all species you can see in the emission. You like to see the densities. That requires absolute measurements, as we will see. Temperatures, rotation and vibration of molecules. But you can also ask the question, which excitation process is there? How do we can measure the production of chemistry, which is the production of radicals and ions? Several processes can be analyzed and give any value if one uses absolute spectroscopy. First, some essentials about plasma spectroscopy. And I'd like to first treat ionizing plasma, which is the typical classical plasma, I would say, because excitation by electrons gives emission, and electrons also ionize and give new electrons and ions. An example of such a pure ionizing plasma is a low pressure molecular plasma for ALD, the group of Professor Kessel's. Here is shown an ICP plasma, and it expands to a lower vessel where the atomic layer deposition is done. It is low pressure, which means that the mean free path is not much smaller than the radius, and therefore all produced ions, radicals, come to the surface. And therefore one can say it is purely ionizing plasma. And here one can see the spectrum in a hydrogen gas. One sees the H-alpha light and the H-beta light, which are indicated, which is the Balmer series for atomic hydrogen. One sees also the hydrogen molecule excited. It's the Fulcher and other bands in the system. As I have said, plasma will be ionized somewhere, otherwise it wouldn't be there. But at other places it will be dying out. And very commonly, as I said, plasma has structure. For ionizing plasma, we can already have some estimate of the electron temperature. And this goes very easy because electron temperature must be high enough to ensure the production of plasma to be equal to the loss. And this gives a relation on the next line, which is that the electron temperature is a fraction of the ionization energy, and the fraction is determined by a logarithmic term of the neutral density, some effective measure of the excitation rate and the time that the plasma lives. And it varies from 4 to 5 eV at low pressure to 2 to 3 at higher pressure. I will use this analysis later to determine the temperature of hydrogen plasma. So for ionizing plasma, the TE is known, but also the ion production you can estimate from similar analysis of the energy balance. In some detail, we will treat now a different plasma. This is an expanding plasma from a thermal plasma source. The reason to do that is that if you have an external plasma to produce the plasma, and different from the recombining plasma, you can have a more effective ionization and therefore more ion production and therefore more chemistry with the same power. So the source is an ionizing plasma with high density, electron temperature about 2 eV, and expansion temperature is there's no magnetic field, is very low, but with magnetic field, and we'll treat both, the plasma is magnetized and there's still current and still partly ionizing. Here you have plasma for processing, and this is how it started. There is a cascaded arc plasma source. This plasma expands into the low pressure and therefore widens up and cools. and in that plasma you seed in, for example, hydrocarbons or silane to produce the carbon and silane particles to deposit on surfaces. And with this machine, very fast deposition has been reached up to 100 nanometer per second. So the first graph is the expanding plasma without a magnetic field. You see the expansion, and that is called recombining plasma, and there's pink light, which is determined by the argon-1 lines, and is used for deposition amongst other solar cell material. On the lower side, we have applied a magnetic field. Now the current can also exist outside the arc, and therefore there's dissipation, and the plasma is considerably hotter, and we see blue light and argon-2 lines. And we will start with this plasma to use some spectroscopy. But first I explain something of the processes in ionizing atomic plasmas. This is what is seen as a classical mechanism. A site with an electron which are hot enough to do that, some out of the electron distribution to the, in this case for argon, 4p for 3D levels and higher, and this is emitted partly by radiation downward. Now, this is the corona part of the system. However, further up, the transition probabilities become lower, excitation rates becomes higher, and therefore you get more a balance between excitation and de-excitation, which is excitation saturation. And even higher, close to the continuum, you get an equilibrium with the continuum, and which is called Saha densities. That is this step from corona via excitation saturation to thermal equilibrium to Saha that we will use to determine electron density later. Here the sketch again in one scheme, and it depends on the electron density, but the density we used right now, 10 to the 20 per cubic meter. Typically the lower states are still in corona, however the other states as 4p and higher are in excitation saturation phase, and the highest states are in Saha equilibrium. Let's look to some graphs. These are taken by Avantes spectrometer, and you see here the black light is the line that's taken close to the source, is the hottest plasma. The red light intermediate at 12 centimeter, and the blue light at 20 centimeter in the colder regions. You can see that in the black and red parts there's still significant argon-2 lines, which means that it's hottest in the 400 nanometer range, so the argon-2 laser lines, whereas at in the blue line it is more neutral plasma with only the 4p, 4s level dominance, 700 nanometer range. If we plot all the levels, which are here 4p, 5p, 4s, 6s, 5p, and 5 and 8s, then we can see that plasmas are above equilibrium, sketched above the Saha line, and the Saha line is obtained with Thomson scattering, which gives electron density and temperature, and therefore you can calculate the Saha density from the formula down in the red block, which means that you can see that here the highest levels are near to equilibrium. And so if we have no Thomson scattering, we could determine electron density from this graph. In the left-hand side, there's still the level densities drawn for several electron densities as measured with Thomson scattering. And you can see they don't change much in density, even though electron density becomes higher. And the reason is that the amount of production of excitation, which is related to the amount of ion production, is not much different because the power is not much different. And therefore only at the higher electron density the highest levels approach Saha, and we can determine electron density from that. Now we go to recombining plasmas. We have no magnetic field, the plasma expands and cools, and electron temperature is too low to ionize and excite. You can see the sketch there. And now most of the light, because there's still a significant amount of light, and this is a warning because not all the light comes from excitation. This light comes from the particle recombination, and this is the only process in atomic plasmas. And you can see that the recombination is though good visible, it's still a weak process in atomic plasmas. And in this case, of course, the higher levels are very close to equilibrium, which we'll see in the next graph. Now there's another point. If we now add hydrogen to this argon plasma, then we will see that there is a totally different spectrum. Because even though there's still argon, we don't see any argon around. All processes are being seen as the hydrogen spectrum, the hydrogen atomic spectrum. On the full right is a logarithmic plot. It's alpha line, it's beta, the second graph, gamma, delta, epsilon, etc., up to H22nd level in hydrogen atom. So there is enough hydrogen that all argon ions are being recharged into hydrogen ions or argon H ions, which recombine in the H N spectrum. And here you see the dissociative recombination of molecular ions. That's what you see. No excitation, but recombination. For the next part, I would like to treat another plasma which is magnetized in the same source and now in much lower pressure. And then the more pressure, that means that there is not so much recombination because of dissociative recombination. And we can see now two parts of the plasma. First, the red parts we saw before, which is the red, it's alpha light. But now we see a blue part appearing further away from the source. I will treat both of them. So line emission by magnetized hydrogen plasma is now partly ionizing because in the red part certainly there is still current coming from the source, and therefore there's still dissipation and still the electron temperature is high enough to excite and to ionize somewhat. However, most of the light you see is from molecular recombination origin. And again, we can only take this conclusion if you measure absolute emission of the HN lines. First, the spectroscopic method used here is that you image the plasma through two lenses. In this case, we used 40 centimeter and 14 centimeter. There's a 1:3 magnification to the plasma, which fits exactly the 1/3 acceptance of the fiber of the Avantes spectrometer. However, this has one disadvantage. We noticed that if the 1/3 image is used, then you can have chromatic aberration of the lenses, which will make that the UV focus is on another spot than the visible and red spot, which would mean you have to do two measurements. If you don't want that, you have to image 1:1. The problems will be less. This is the Avantes spectrometer we used. And now we first treat the ionizing plasma in molecular hydrogen at low pressure with magnetic field. And here is the spectrum. And so this is in fact two spectrum, one to 400 meter and one from 400 to 800. And you see clearly first the H alpha, H beta, H delta, H gamma lines. And you see the top curve is close to the source, and then the pink curve is further away. And it's 4, 8, 12, and 60 centimeter from the source. You see on the left-hand side that you have a strong, what is called an hydrogen molecular continuum. And this is actually the same emission which is used in the hydrogen or deuterium lamps to calibrate the spectrometer. It is a strong continuum, and I'll come to that in the end of the end of this presentation. But first, the Fulcher total emission. Yeah, the Fulcher emission bands is indicated, and this molecular hydrogen band is the result of direct excitation by electrons from the hydrogen molecules. Since you know the pressure, you know the temperature, you know the hydrogen molecular density, and therefore with the formula the electron density times the molecule density times some measure of the excitation rate times the exponent in the excitation rate, you get a measure of the Fulcher excited state density. In this case, it is electron saturation case, So the levels are not mainly de-excited by radiation, but they are mainly de-excited by excitation upward further in the hydrogen molecular system. Which means that in this graph the electron density drops out, and therefore the electron temperature is obtainable from a logarithmic expression of the hydrogen molecular density, and therefore is rather precise. Now if we have the electron temperature, then we can determine the H-Balmer lines, ionizing plasmas, and then we can at high lines measure the electron density from this approach. Here is a graph from the red close to the source at 4 centimeter, and we see here that the low-lying lines, n=2 in this case, is measured by absorption spectroscopy, and 3 and higher by emission. You can see that the first levels are much higher than the Saha line, but you can see that at the higher levels they approach the Saha line of limit. And if you take that limit to be the Saha limit, then you can calculate what the electron density is, assuming the electron temperature from the Fulcher measurement. Here is another measurement at 60 centimeters, still in the red, still the same spectroscopy, and here you can see the Saha approach already pretty well, because the highest level are close to each other, and you get electron density and temperature. Now here's again the graph, but now including the blue part with the absolute densities of the excited states. As I said, the black line is the n=2, which is measured by absorption spectroscopy, which is not treated in this seminar, but the other lines are all measured absolute levels, which are measured by lateral profiles, inversion by Abel inversion, and then having absolute densities at axis. In the blue part, then there is not much dissipation left, but still there is significant amount of light, and it's absolutely blue. Now this can only be because apparently the blue lines of the H-Balmer series are much stronger than the red lines, which is the Fulcher band and the H-alpha series. And this means that there's inversion in the atomic system. And this gives automatically inversion. That is the main process, is the recombination of H2 plus ions at H minus, which gives a resonant level in n=5 or 6. And the H2 plus and H minus are all originating originally from the low vibrational excited hydrogen molecules, which come probably from the surface. Now here you can see, because if you now this is of course only a spectrum which is calibrated, but still you have to correct for the transition probability and the statistical weight, but you can see already that 5 and 6 are much stronger occupation than 3 and 4, if you take account of these. And that means that there is input in the 5-6 levels because of this process of recombination. And this is again an example that this is not excitation by electrons from the ground state, but this is excitation from above in a recombining system, and in this case a molecular process. Note also the NH band and the OH bands in the 300 and 337 ranges, which are also clear signs of molecules entering the plasma, and we'll come to that later. Now the results of the magnetized plasma of low downstream pressure can be summarized as follows. Here on the left-hand side is the left part is in red is the electron density, and in black is the electron temperature. The electron temperature on the axis ordinate left, and the electron density ordinate right. And you can see that this matches quite good with the probe measurements, classical probe measurements in the blue part. The probe measure could not be performed in the red part because the probe becomes too hot. And you can see that this indeed, when one measure absolutely, we can replace Thomson scattering and can replace probe measurements by classical absolute emission spectroscopy. Now let me say one other thing. This is the Fulcher band you can see by the standing Fulcher on the right hand side picture, besides the H-alpha line. And you can see several other hydrogen molecular bands at around 700 nanometer and around 400 nanometer. And again, at the lowest wavelength in the UV, you can see this strongly increasing hydrogen, molecular hydrogen continuum, which I come to in a moment. This continuum arises from excitation from H2 to the lowest excited state, which is the small a triplet state, and this triplet state can radiate only to the triplet ground state, which cannot remain because it is forbidden state, and therefore it falls apart in a dissociating action. And therefore it is a quasi-continuum which starts in the UV at 190 nanometer. There is also a two-photon continuum, and for the rest, it was actually the start of this whole research are the free and free bound research, but it appeared that molecular continuum, in this case, at least in the lower wavelength range, is much stronger than the classical free and free bound. And again, to reach that conclusion, you must have absolute intensities. Now here is plotted from Vans, but it has been replotted in a logarithmic way, the emission strength of this free bound emission, which is to fact somewhat dependent on the vibrational population of the ground state of hydrogen molecule, but it is not strong, and you can see there's a logarithmic dependence on the wavelengths, and so it's strongest in the 200 nanometer range. Now here again we can see it that in the left hand side is the 300 nanometer, it is strongly increasing as indicated. Then at 400 nanometer there is still this molecular band. At 600 is the full Ger band, and higher is the 700 nanometer band. So maybe only at the 500 nanometer it approaches the hydrogen bound free continuum, which could then also give a measure of the electron density. But for hydrogen, this is not a very strong way. You could use, of course, the hydrogen molecular density to absolutely calibrate your optical system if you would know the hydrogen density and the excitation from the full Ger band. For the last part, I'd like to indicate some molecular signatures. And again, what you see is not what you see, because you can see here the OH bands, which are at 300 nanometer and somewhat below. These are strong bands. This comes from OH excited molecules, and there is a line at NH, also an excited state from NH. Now this is not the emission from OH and the emission from NH. No, it is the production of NH and the production of OH. And the processes are charge exchange. So the ammonia molecule charge exchanges with H plus, produces an H3+, and H3+ falls apart in dissociative recombination in the NH excited molecule. And the same for the water molecule is produced on the surface. And hence you can see also that the magnitude, even though this logarithmic scale suggests at the lowest to be stronger than at the highest, but if you see that the scale is of course changing, it does not change much with electron density. And it means that with this way you can have a kind of measure of the water and ammonia production in this plasma. This brings me to the conclusion. Look to the plasma because you can already see with some knowledge of plasma physics, of recombination and excitation, what kind of species are in your plasma if you look to the spectrum. Measure absolutely. It does not take much more effort to do that. Of course it takes an effort, but it gives you a lot more information about the absolute levels of excitation and therefore the absolute levels of production of ions in the ionizing phase and the strength of recombination, the recombination phase. And it is important to measure activity, since at the end it is not NE and TE, but the production is what you want to know. You want to know how much chemistry can I produce. And you need info of the system is ionizing or recombining. You need system on collision radiative phosphosis, but then you can get fast and with little cost a precise and complete picture of your plasma. Thank you.
This brings us to the end of the presentation part of this webinar. At this point, I already want to thank Daniel for his part in contributing to this webinar. And we are now open for the question session. In the meantime, we already have a couple of questions, but if there are remaining questions, you are now able to put them in the chat box so that we can answer these questions. Then we go to the first question. The question is, for detection of plasma without fiber, so directly exposed to radiation, is there any injury to the CCD? I think I'll take that part, but if Daniel would like to comment, it's also possible. But in normal metals, all CCDs have a certain threshold damage. But in my experience, the plasma levels of intensities are not in the range that they damage the CCDs. Then I have another question. What is the minimum electron density for which this method can be deduced? I think that would be a nice question for Daniel to answer. Daniel?
I will answer that because in this particular case I presented is a relatively high electron density compared to more classical plasmas. And then these absolute measurements come into play to measure the approach to SA, and therefore you can measure electron density. At low electron densities this is not so easy.
Unmuted.
In that case the system is more in corona, and therefore you can use alternatives to determine the ionization rate essentially, because the excitation of levels is then a function, is related to the amount of ionizations per unit of seconds. Again, then absolute spectroscopy will give you more information than relative. I hope it answers your question.
Okay, thank you, Daniel. On to the next question. When you explained the grating, you mentioned that the direct reflection and other orders will not hit the detector. How do you prevent this? I think I'll take that one, and for that I can best go to one part of the presentation where we show the model of the spectrometer inside. Preventing these other orders coming from this grating here, we have made a design in a way that we have such light traps here. We call them compound parabolic concentrators, and rays getting into these parabolic shapes will be extinguished in a certain point, so therefore they cannot hit the detector. I hope this answers this question. Then I have another question. How will the detector surface be protected against contamination from the plasma? Good question. I'm thinking if it would be in my corner or in Daniel's corner. Daniel, do you have an answer to that, or do you want to leave it at our...
I leave it to you for the moment. I can see whether I can react.
Okay.
Because is now the question that to measure the impurity level in plasmas?
And the question is more that if measuring plasma will cause a certain degree of contamination inside the spectrometer. So,
Okay.
But in my
for
opinion,
me difficult to answer.
Yeah, I do not know the answer by 100% sure, but in my opinion it are the photons which are getting into the spectrometer, same as normal light conditions, and that no contamination will take place. If there are surroundings that materials enter the spectrometer which can cause contamination, then in theory it could be the case, but in my experience it's not. But I'll take a note on it. I've seen who has asked the question, so if you can find further information on that, I'll take the liberty to contact this person directly. Then I have one other question. Is there a systematic approach for the determination of plasma parameters possible? I think I'll bounce that to you, Daniel, if you can answer this one.
Now, in a certain sense, yes, but also
Muted.
But it depends on the electron density. I think, roughly speaking, you could say that an approach is possible in the corona part, which typically electron density is up to 10 to the 17th per cubic meter, in which, like I said, most of the lower levels are radiation dominated, and therefore in that case the temperature is also usually higher, so the amount of excitation which you see in the radiation is coupled to the amount of ionization. So not so much the density itself, but the ionization rate.
Unmuted.
The recycling rate. If you go to intermediate densities in the range of 10 to the 20th, as described in this webinar, then I guess in most cases you can get radiation from high light which are close to SAR and therefore obtain the electron densities. And there is also a little bit more systematic approach possible, because if you plot the excitation levels
Unmuted.
Against ionization energy, you will see that there is a decay which in which the difference with the SAR density decays, and then if you work out in principle you can make a good guess. At high electron densities it is easier, of course, because densities approach SAR, and then also other methodologies as broadening with the Lorentz broadening by the Stark effect becomes possible, and otherwise also the continuum radiation, which was not treated here, because in this case we treated it was totally overshadowed by the molecular radiation. I hope it answers your question.
Okay, thank you, Daniel. Questions keep coming, so there's an enthusiastic public there. Next question is, thank you for the presentation. I have used a spectrometer with high resolution, but not absolute irradiance calibrated. I observed much background level. Then there was an error in measuring of the H-alpha bandwidth. How can I reduce the influence of background emission? Daniel, is that something?
Yeah, it's of course a methodology approach, but yeah, let's say Avantes promised that there is not much higher order problems, right? So in that case, I would also expect that the background radiation from zero order would also not be strong. But if so, of course, you can use a filter.
Okay. And yes, we try to keep up our promises to keep our spectrometers free of other orders. And yes, we have different configurations to put in filters to reduce other effects.
But I think anyway it would be wise to have some filters around to test that.
Okay. Then I have a final question. What is the advantage and disadvantage of using fibers instead of direct exposition, as direct measurements make our spectrum more stable? In my opinion, it would be the geometry and incoupling of the spectrometer. But Daniel, do you have comment as well?
No, yeah, of course, in my group there has been enormous history with using classical spectroscopy, also for more elaborate methods as Fabry-Perot interferometers. In that case, we learned to use classical images. However, I must say that my experience with this imaging on the way I described is not bad. The only thing which really was hindering was the chromatic aberration, which hindered the calibration significantly. So if there would be a simple imaging system on the fiber, it would be very helpful, I guess.
Okay.
Maybe with a mirror rather than a lens to avoid the chromatic problems.
Okay. That brings us to the end of the list. So again, I would like to thank you, Daniel, for contributing in this webinar. And also I would like to thank all the attendees sitting their precious time listening to this webinar. We hope it brought to you what you expected, and we hope to see you back at the next webinar. Thank you very much.
Muted.